My name is Micah Perez, and today I'm going to be running through my final parallel program um, to kind of give you an outline of what I'm going to be talking about today. First, I'm going to be going through what I decided to do, which was hash cracking, what it was, and why I wasn't interested in it initially. The sequential code that I wrote, and I'll go through that line by line. The parallel code, how I implemented this, and what kind of problems I ran into, using MPI and why I decided on MPI out of all methods of parallelization, the speed up that I was able to get, and then finally some final thoughts on the project itself. So to start, motivation, I kind of based this off of HashCat, which was an existing program that I've used to crack certain hashes. HashCat's a really cool tool. What you're basically able to do is put in a list of existing hashes and a word list and run it through HashCat, and it will try to brute force crack most of the hashes and check if there's any pairs. So I try to model my program as kind of a simple HashCat that I fully built. I guess to explain deeper why I'm into hash cracking and kind of how I originally got started with this was through a couple of my security classes. They taught us about using hash crackers like this and kind of doing it to crack passwords. It's something I always found interesting. And right here, this is a security competition that I've participated in the last 3 years. And one of the kind of major sections of the security competition is password cracking, which kind of will typically give you a list of hashes and see if you can crack these using tools like HashCat. So that was kind of my initial motivation. I was interested in kind of doing this project because I felt like it's something that I've used before with kind of parallel or a sequential code, and I wanted to see the speed up that I can get by making it parallel. And I felt like this is something that is almost embarrassing parallel in a sense that the majority of the operations could be speed up via parallel computation. So I guess to kind of start, I can run through my sequential code that I created initially. So I'll make this right here. I coded this in C++. I decided that just because I'm a little bit more familiar with some of the extended tools and libraries of C++ other than C or other languages. But yeah, I can go through the code. One thing to note is that I did not write the MD5 hash algorithm. This is something that I got online that I do use in my code, but what this does is it takes a string and it outputs the MD5 sum hash of that string. So obviously I needed this for the HashCracker. But the main sequential code, this is something I didn't base off a word list. I wrote it all myself. So this takes two arguments. It's going to take an existing file of hashes, and it's going to take a word list. And that's if it takes any less or more, then the program's just going to error out because it needs only two arguments. So the first thing that this does is run through the input file for the hashes, and it's going to put all these in a vector. So that's just some pretty kind of simple I/O. This couldn't really be parallelized, and I didn't think it was worth parallelizing it since it wasn't the main kind of bottleneck of the program. And typically this is done pretty fast because lists of hash you need to crack typically aren't the biggest in my experience. But this is kind of the bread and butter of the project, everything below here. So what this is, and this is also kind of where I started timing to see how long the program actually took for increased accuracy to notice my speed up. So what this does is it opens up the word list, and then it takes the number of words in the word list, which is one other thing that you're going to have to do, is put how many words are in the word list as the first line of the word list. And then it's going to run a nested for loop. So what this for loop is going to do is it's going to get each new line of a word list, which might be some massive file with millions and millions of lines, turn that value into an MD5 string, or an MD5 hash, excuse me, and then it's going to run through your existing vector and check if any of those hashes are equal to your existing vector. If that's the case, then it'll output the hash and then the cracked word, so essentially what word is equivalent to the hash, and then it's going to pop that from the vector. Now if all these are cracked, then the program will end, it will get the output the time it took, and then it will kind of exit out. And if all the hashes aren't cracked, then the program will just finish up down here and then also return. So either way, it's going to run through the entire word list and try to see what files can and can't be cracked. So I could give you an example of running the sequential program right here. I'll run my executable. I'll specify my word list. So I made 4 example word lists. This third one is kind of fictional characters, based on like passwords based off fictional characters. And then I'll specify my word list. Excuse me, these are where my test hashes, which are fictional characters. And then my word list is the Rocky word list, which is kind of the flagship word list for hash cracking. It has over, I think it's almost 15 million lines of code. So it's definitely, lines of words. So it's definitely not the smallest file. We could run this and then see that it shows my input file, my word list file, and then it's going to run through these hashes and give me the hashes that it cracks. So even though this is like 15 million words, it's still decently fast, just kind of given the speed of the C language. But I knew that this could definitely probably be speeded up at least a little bit with some parallel code. So that was kind of an example. To further test this, I actually wrote a test script which would run through each of my tests multiple times and would kind of give me the output of each of those times. So right here, and then I could add those up, making it easier for me and automating some of the process of testing the code. But I guess the important part to look at is the actual parallel portion of this code, which is obviously trying to see what I can do to speed this up. So I'll make this right now. Again, I did use C++, so I had to, instead of using just the regular MPI CPP, I used, or the regular MPI, I used MPI ICPC, so that's specifically for C++. I can run this, or so then we can look through my parallelized code and kind of see what I decided to do different. Now, one thing to note is that the first kind of problem I came across while writing this program was I realized that file I/O is very difficult, if not impossible in a lot of cases, to parallelize, and that is a large part of my project, or that is a large part of my program. So I'll explain kind of what I did in a second, but at least for this first part of code, it's pretty much the same, almost the exact same as the sequential portion. You're just reading in that initial input file of hashes and then pushing those to a vector. I start at MPI right here. I initialize it, I get the rank, and then I get the size. I start, of course, my MPI so I can time the program. So this was kind of my difficulty right here, was figuring out how to most efficiently parallelize the I/O. And what I did for this is, this was part of my motivation behind putting the amount of lines in the current file as the first kind of argument of this file. So that's what it's doing, is it's reading in the size of the input word list. And then what it's going to do is it's going to divide the entire size of the word list by whatever your current rank is, or excuse me, by the amount of processes currently going on. And then it's going to get your starter line number by multiplying your rank by the line amount, right? So if there's 10 million lines, for example, and there's 4 processes, then each process is going to get 2.5 million lines to iterate through. Now, one other difficult part of this was realizing how to actually get the input to that line. So right here, I just wrote a kind of dummy for loop, which will just get line, but won't do any calculations until you're at a certain the point that you want to be based off of your rank and the kind of step size of the line amount. So this is kind of where the parallel portion comes into play in this nested for loop here again. And it's, again, this double for loop, but this time it's only running, it's not going through the entire word list, it's just going through whatever portion that certain process is kind of dedicated to, and it's going to look through all those lines of code, crack or run the MD5 hashing algorithm, and then compare that. Now, one problem I did find here was that I couldn't do any tricks like I could in my sequential code, where I could end the program early if all the hashes were cracked. So this just completely runs through the word list for each process, and any way you look at it, it's going to be running through the entire word list. But it's still obviously able to be parallel because that is most likely going to happen either way, unless all the hashes are in the existing word list. And then what this does is this waits for all the existing processes to end. And then once those are all done, it will output the time it took to run the entire program. So that is my parallel code. And we can actually test this. Right now I have excuse me. So we had to specify the hosts, but we can actually test this. Right now we'll use 4 unique hosts, run 2 processes on each host, divided by for each core, and then use that word list right here with this argument. Run the program and then specify the hash file. We'll use the same hash file that we did before, and then the word list as well. This doesn't seem to be working with the host right now, which is a problem I've had before. So I'm actually just I'm not going to specify this hosts file, since sometimes that won't work. But as you see right here, it's running through that hash file. And this time it took 9 seconds to complete, which before, I believe it was closer to 13 or 12 seconds. So there was definitely some speed up. While I was testing and running the script on different nodes, I was actually getting even more speed up, which I could kind of show right now. So I guess the one thing I didn't mention was why I decided to use MPI and what my motivation was behind that. I wanted to use MPI so I can get kind of more experience with distributed memory. I felt like I've already had experience with pthreads and OpenMP and that shared memory, but I felt like this is something that can actually benefit from distributed memory, and I like working kind of across different processors and all sending it back to kind of that main machine running your code. But as for kind of the speed up that I noticed while running, while doing the testing, this was kind of Amdahl's ideal speed up that you're going to get right here, which obviously, twice as fast with twice the number of cores, ideally, and then, 4 times, 6 times. And then this is what I got. So when I ran it with kind of 8 processes going at once, I got just over 3 times the speed increase. I did get a little bit of a speed decrease when I ran it with just 1, which is essentially the same sequential, just you're doing all the overlap with the extra MPI code. But just from using 2, I immediately noticed that speed increase. So I definitely felt like this project was, I was able to see some increase within this. I also made some graphs right here in my report, and it kind of reflected some of my testing. So when I used 2 processes, I got a certain amount of speed up, 4 processes, and then obviously, this kind of evens out as the more processes I use, because there's only so much speed up you can get with a program like this. This is actually pretty interesting. This is my running it through my sequential tests, and typically I would get an average of around 35 to 36 seconds. And then while running it with my parallel code, I get an average of 29 seconds with 2 cores, 16 seconds with 4 cores, 12 seconds with 6 cores, and 10 seconds with 8 cores. Now, of course, this was at a different time of day, so the times will change depending on who's on the nodes, but I found it interesting the amount of speed up that I was able to achieve by using more cores. So I guess to wrap it up, that was my final parallel project. I definitely felt like I used a lot of the material that I learned about in the class, and that I was happy that I was able to speed up the existing kind of HashCracker that I wrote sequentially. I do think MPI was the right tool for this job, but I'd be curious to see how something like OpenMP or pthreads fared in the future when compared to this MPI. I do think that MPI might have been the best in terms of dividing up the work between process sizes, and that I already got some experience doing that kind of before in the class. But yeah, this is definitely a project that I'm happy with, and that I felt like I got a decent amount of speed up in terms of cracking the hashes. So thank you, and have a nice day.